between vendor A equipment and vendor B equipment with optical fiber. And a full set of parameter definitions and associated values at interface point MPIS, multi-path interference at the source, and MPIR interface at the receiver are necessary to enable such an interface. Very simple thing. And as I said, longitudinal compatibility means that in this case, vendors are same. So we don't need to have an interface between the different vendors because this is the same vendor. Yeah. And the specification also allows the deployment of a system from different vendors on the optical fibers of the same cable. And a limited set of parameters, and usually only the characteristics of the optical path are specified. That means because this vendor and this is the same vendor, so once we provide this fiber optical path parameter are given, they can manipulate within their equipment. We don't need any detailed specific interface because not multi-vendor, but single vendor. Okay, this is the so-called longitudinal compatibility. And another term in optical fiber handbook describes joint engineering. A bit tricky word, joint engineering. Sorry?
Yeah, it's okay. Okay. So for this vendor A and vendor B, according to ITU, is it possible to take, for example, an equipment from Japan Telecom, I don't know, use it as A, and then connect it to France Telecom equipment as a B in the same network? And do the configuration, drop and add the services without any problem, with the same enemies. Yeah, for example, if I have a Korea Telecom equipment and I have a Deutsche Telecom equipment, one is A, another one is B, according to recommendation, IT recommendation. Is it possible now to connect and in the same network?
Your question is actually if you have two vendors from this side and this side, actually, is it possible to connect? Yeah, actually, ITUT recommendation have offers such kind of interoperability. So in a case, for example, this is 40 kilometers of optical fiber for G.652, like that. Then you place here vendor A. Of course, this vendor has to be complied with this G.959.1 or any recommendation specification, output power or spectrum or something like that. And the other vendor B also complies the same recommendation G.959.1 or so, and they have also the same specification here, MPIR specifications. And if this is a kind of 80 or 40 kilometers fiber anyway specified in the recommendation, of course you can connect these two vendors. Yeah. Okay.
Two different equipment from two different vendors. In terms of network management, is there any recommendation from ITU?
Yeah, very, very good question. This is a very problematic point. even if you can connect a physical layer, fiber, SDH, the management system is different one. Because it's very difficult to integrate management system between the different vendors because this is software. Hardware is rather easy to make specifications like a power or wavelengths, it's easy. But operation system is created by software. Software is very, very complicated. For example, you can't use, for example, Windows or Mac computer or like OS is different where once you have another software for word processor or something like that, you can't use another products of software. So software is very, very difficult to make compatibility. And most cases, you will have if you have the two vendors in your networks, actual signal can be connected, but the operation system cannot be integrated because vendor A will say, I don't care about vendor B system. Vendor B may say, I don't care about vendor A. So in such a case, two solutions is that you can have two operation systems, two screens, look, vendor A, vendor B, and any trouble, you will check vendor A's screen, the trouble or something, and the other trouble, you can check the vendor B's operation systems and look at which is correct or which has trouble or something, right? Another choice is that you will have NMS, or do you know, network management system. So we call this is AEMS, elementary management system. Elementary management system operates the equipment, but we can also have some network management system that can supervise the elementary system. So if you have such an NMS that can totally supervise the network that contains the EMS of vendor A and the EMS of vendor B, in such a configuration, you can look at the whole network that includes vendor A and vendor B. Okay? Oh, okay. I see. Any question? Okay.
Yeah. The question is actually rising from the one that you just answered. If you're suggesting that the general NMS might be able to help, the general NMS is actually, it's software. It's software. It doesn't really, it doesn't always have the capability of handling any kind of problems. So you might end up having the same problem if the NMS, the general NMS, to manage the whole network is not taking into account the problems that you're having locally.
You are right. And this problem is always a really headache problem for carriers. Yeah? Because vendors don't care about the other vendors' systems. Okay? So there is no way other than we will have a so integrated supervision system like NMS. I don't know any good answers for your question currently. This is not for you, but all the world carriers problem. Okay, so very easy answer is just you create your network with only one vendor. Yeah, but under such a conditions, no competition, and the cost will rise and rise. So we are said catched by the vendor. So you will have no choice other than one vendor, the cost will increase. But if you have 2 or 3 vendors, your network operation will be complex. So which do you take? No clear answer. All right. Okay, microphone, please. Oh, okay, okay.
Yeah? Okay, got it. So what you mean is that troubleshooting now always happens, let's say like the configuration changes have to happen on the EMS level. Because if you're going to have an NMS that just for observing and you can't do much more. So basically, all you have to do is to rely on the EMS.
I don't catch your question exactly. But
Okay, what I'm saying is that for each vendor, you're going to have an elementary management system, as in for that vendor. So which means most of the troubleshooting work will be done on the EMS level.
you may discuss each other. No problem. Actually, I didn't mention the about supervision or elementary management or network management or operation issues because this tutorial is just on the optical fiber cable systems and kinds of like that. But anyway, I can answer you. Sorry.
Yes, I want just to go back at my question. You know, in industries, you have before you had like a system called PDH, and every vendor had its own PDH system. Then they started with to produce like Sonnet and so on. American, Europeans, and Japanese had their own system. Now the ITU sets an international standard, like the SDH. Now, in terms of software, is there any standard on EMS, on network management, so that whatever system you have in optical system, you can manage with that NMS? That was my question.
Okay, actually, there are some standardization organization on the telecommunication management systems. In the past, ITUT has a so-called SG4. SG4 was concerned about telecommunication management systems, but now SG4 disappeared and included in some SGs or so. Sorry? Oh, study group 2? Okay, I see. Yeah, management, yeah, study group 2 issue. So I don't remember exactly. But anyway, outside ITUT, there is so many standardization or forum about the telecommunication management system. Like a TMF means a telecommunication management forum. If you are interested in a management issue, you will, it may be better to join such kind of forum or something like that. And also, your question is just how do you operate with the EMS system? But actually, not optical layer, but SDH or OTN layers, there is a standard for alarm indication signal or something, alarm transmission schemes, standardized schemes. So even the different vendors, they can communicate something happened in my network to other network domain. There is such kind of alarm information exchange system is standardized. And actually, we can use such kind of information for troubleshooting. But actually, detailed manipulation like a EMS system cannot be standardized because, as I said, this is just a software oriented system. So as you can see, we can use all the same Windows operation system, so we can exchange information easily. But if the OS is different for each other, we can't communicate. The same situation. EMS cannot be integrated only one standard or one specification because there are so many vendors. Of course, some vendors says the vendor will make all the EMS or NMS systems, so just follow me to other vendors. But I don't think it's not successful. Yeah. Actually, this is so long history. There was so long history about this such kind of management issues, and still we have so problematic issues. This is because in history, in the past maybe 20, 30 years ago, telecommunication carriers, only one carrier each country. Like in case of Japan, only NTT was a telecom carrier. In USA, only ATT. In France, only FT, like that. So in such a case, we have to make our own operating system, and some vendors, 3 or 4 vendors, made the same system, same specification under the instruction of NTT or telecom carriers. So we don't have such a problem of interoperability between vendors. Only the problematic thing is that international communication between USA and Japan, but it doesn't care about so much. Okay? So yeah, your question is a really, really good question, but at this moment, I don't have any clear, good solution for your question. Thank you. So, okay. So the slide stopped there. By ITU recommendation, it's not sufficient to cover your need for optical interference. So in such a case, so-called joint engineering can provide a means to improve the link performance to meet the specific operator requirements. So this will probably be done in those cases where the required section loss is greater than the specified, standardized. But it may also be considered for other parameters. So up to the operators to specify more closely the aspects of the system where the specification or the relevant recommendation is not satisfactory. That means in some system you can't meet the standardized specification, but in some cases you can have such a joint engineering with vendors and the carriers. So even the system doesn't satisfy the standard. There could be some cases you can achieve to make a system outside the standardization. So every situation requiring joint engineering is likely to be different. So it is for the operators, manufacturers to come to an agreement as to what is required and as to what is actually feasible. So this process is very likely to lead to both ends of transmission link being supplied by the same manufacturer who meets the required performance by jointly optimizing transmitters and receivers. So for jointly engineered systems, it would be advisable for operators or manufacturers to follow the general guidelines and the system engineering approach used in the ITUT recommendation. That means you should use definition or parameter of definition according to the ITUT recommendations as a common language between the operators and vendors. Even your system don't meet the ITUT recommendation. In such a case, you can use some part of ITUT recommendations, and the joint engineering can make your system if you cooperate with vendors. Not so special things. So I will stop here, and how about have a coffee break, okay? And 15 minutes, and we will resume 3:30, okay? 330, okay? 335, okay. Thank you very much. So, shall we start? Already 15 minutes to 4. So, we should start now. So, continuing in chapter 6 issues, and this is the specification methods. One of the specification methods is so-called black box. But the idea is not so difficult. Just black box means that this contains any specification or parameters, but we don't care about the details of configuration. Just we can define the black box parameters at this output interface point and at this interface point. So we don't care about the inside this like optical multiplexer loss or TX power or something like that. We don't care. But we only specify at this point. So this type of specification can be some freedom for vendors. Vendors can accommodate inside the box freely, and only the outside this point can be specified. So we say this is a black box. Another specification method is the so-called black link. Black link is just black means just we don't care about the box or link. It's okay. So we say black link or black box. So in this case, black link is from a single vendor. In this case, single vendor means this black link is provided by a single vendor. And we will have a vendor A, B, or something transponder, and we will interface point here, and here fiber, and here this point and this point. So we don't care about this inside specification inside of this box, but we specify only this interface point or power level or wavelength or something like that. This configuration also gives vendors freely design their own specifications inside this black link. So we don't care about this inside configuration of this box or specifications. So we say black link specification. So this figure shows the example of application codes. So application codes are so many combinations of channel counts or optical tributary signal types, span distance fiber types, and system configurations. The structure of these codes varies from one recommendation to another, depending on the characteristics required to distinguish one application from another. Bitrate and the type of fiber are common to all of the recommendations. So all the recommendations are, with the exception of those covering black link applications, the application code includes some indication of the distance. So normally this most simple application code described in G.95957. You will see such a code L16.2. That L means target distance. L or S maybe 40 kilometers, L is 80 kilometers. And 60 means STM16 bit rate, so 2.444 G. And 2 means G.652 in the 1550 nanometers region. So you will see L-16.3 if we use G.653 like that. But this target distance approximately 80. L means 80 kilometers, and approximately 40 kilometers in the another wavelength windows. But you have to care about that these target distances are for classification purposes only, and do not guarantee that the link of that distance can be accommodated or conversely, that the link that is somewhat longer cannot. Okay, so it depends on the situation. And anytime you can use 80 kilometers or not, it's not correct, but just a specification purpose. And in this figure, so more complicated example of application codes. This is used actually G.698.2. Recently, ITUT standardization specifications are very become complicated because we will have some complex optical devices inside the network or line. For example, optical add-drop multiplexing or something others. In the past, we had only a fiber between the equipment, but recently we have like a PXC switch or OADM, so complicated. So we need such a complicated application codes. And so maximum attenuation that the link must have the limits for chromatic dispersion or DGD. So very complicated numbers are added for recent application codes. And for example, this is a DN100C-2A3LF, like a DWDM, narrow spectral excursion, minimum channel spacing is 100G, and chromatic dispersion limits appropriate to compensate or highest class of bit rate is 10G. 2 means the OTN rate 2. OTN 1 is 2.5G, and OTN 2 is 10G, and 3 is 40G, so 2 is 10G. A means amplifier is included, and fiber is Z.6535. And the operating wavelength range is so-called L band, not C band, L band. And the FEC was used. This is just a simple case interface point at MPIS. MPIS is a main path interface and sender. This is just an interface point at this sender side. And this is a receiver side, very simple. And this is just an interface for a multi-channel system. Because this multi-channel WDM systems, the signal can be multiplexed, and at this sender point, you can see only the multiplexed signal, not only single wavelengths, but multiplexed channel. So we say MPI-SM, and the receiver side MPI-RM. M means multi-channel. So I have described the interface point. So then the interface at point MPIS and MPISM output power. This is just a simply a parameter, one of the parameters at MPIS. So output power normally specified by maximum or minimum mean channel output power. That launched power for in each optical channel is the average power of a pseudo-random data sequence coupled into fiber from the transmitting equipment. That means, as you can see, actually digital signal or NRZ or RZ are modulated with a random pattern. So peak power, there could be two types of power definitions, that peak power or average power. Average power means that digital on-off, on-off, so normally half the power of the peak power. Yeah? So that means pseudo-random data sequence means the average power over random data. Okay. And it also gives the range maximum or minimum to allow some cost optimization to cover allowance for operation under the standard operation. That means that just only fix the level of power, not fix the power, but some range of power defined for cost-effective equipment. This is just maximum mean total output power is the maximum value of the mean launched total optical power at point MPISM, just the sending side interference point. So also at this MPIS point, source type are defined. Depending on the attenuation, dispersion characteristics, and the hierarchy levels of each application cause feasible transmitter devices use, as I described, LED or multi-longitudinal mode laser or single longitudinal mode laser. So recently, we will have to care about only this single mode laser. So each application, the recommendations indicate a nominal source type, but it is understood the indication of a nominal source type in the recommendation, not a requirement. This is not a requirement, but just a specification. Important thing is a single mode or something, just a specification. Recommendation doesn't say you should use laser or LED or something like that. So SLM single longitudinal mode devices can be substituted for any application showing multi-mode as a nominal source type without any degradation system. This is a really rare case, and actually you don't need to care about it. Next one is so-called interface at point MPIS and MPISM extinction ratio. Extinction ratio is actually defined by this equation. This is the ratio of optical power level at the center of the logical 1 to average optical power level at the center of the logical 0. That means just level of exactly 0 versus level of some 0, actually some amount of difference between the 0 and the actual pulse 0. So sometimes this extinction ratio is defined in optical transmission systems. But actually, a more important thing is so-called I diagram. I diagram is as the interface sending side. You will see a transmitter waveform. And as indication of the quality of an optical signal can be achieved by measuring I diagram. This is an I diagram. And this I diagram actually fits the mask pattern. I will describe later mask pattern, but anyway, this I diagram have to meet the I mask. So measurement could be carried at any point on the optical fiber at the beginning. That means a transmitter, output of transmitter, or middle, or receiver side. And in particular, at the end of a link, the optical eye contains all distortion effects or something like by transmission of the fiber. So the signal quality for optical interface is qualified by the definition of the eye mask for the signal at the transmitter S-type reference point. That means this is so ideal I pattern, ideal. So this is a bit rate. Actual signal is a continuous sequence of 1010 pattern, but this I mask is just a superposition of each bit time to one figure. So you can see this is 101 or 010 pattern. So this is just a superposition of the many digital pattern of signals. So you can see by this eye how the signal, optical signal is degraded or not. Actually, this is so-called eye mask pattern at the sender side optical transmitter output. As shown in this figure, you will see this mask pattern. This small number will be defined in each recommendations. And as you see the previous figure, that you will find such an eye pattern of optical signals. And the specification is that this pattern should not cross this area. If the waveform degraded by the fiber transmission or something, that you will see more 3pi like that. And the line will take this, pass through this mask pattern. So such a I pattern is not accepted by this recommendation specifications like that. And also, this figure shows a so-called RZ pattern. This is NRZ, non-return to zero pattern, but this is the RZ pattern. So different style of mask was defined for RZ pattern. Okay. This is just an example of another eye mask pattern, but now currently under discussion. The reason I showed this figure here is that we are now discussing in ITUT as another mask. Eye mask measurement method is discussed in also IEEE. IEEE are concerned with Ethernet, 40G or 100G Ethernet. So they are using such kind of a more complicated mask pattern. And this mask pattern is a conventional method defines no signal exists in the mask, but this mask accepts no signal, but some amount of error. For example, 5 cross 10 to the power of -9 region. Here it is. So you can have more loose specification for this with these masks. So this leads to be a cost reduction of equipment. So now in ITUT we are discussing such kind of masks, or instead of clear specified this type of masks. Yeah, next one is just I described about the specification of sender side MPIS line. Then I will describe so-called optical path. Optical path defined between the MPI sending side and MPI receiver side. So between the sending side and the receiving side, we define the optical path. So-called first one is attenuation. So the first one is optical attenuation. Of course, as you know, this is just minimum or maximum path attenuation loss in dB between the sending and the receiving side. And the end of life condition of the BER of 10 to the power -12. And this attenuation specifications are assumed to be worst case values. That means the loss is due to splices connected, all inclusive. Yeah? And additional cable margin to cover allowances like future modification of the cable configuration or fiber cable performance variations due to environmental factors or degradation by any connectors or something like that. So maximum attenuation values are required in G.695.959.1 based on the assumption of installed fiber loss. This means actually installed fibers loss. Of course, include the splice and the cable margin, but actually we use this value 0.275 dB per kilometers or 0.55 dB kilometer at 1310 nanometers region. As you know, that's 1500 region has a lower loss than 100,000 nanometers region. So attenuation spans are defined such as 11 dB for 40 kilometers and 12 dB for 80 kilometers at a longer wavelength region, and 11 dB but 20 kilometers or 40 kilometers for shorter wavelengths. Okay. This is also a specification for optical path. So maximum chromatic dispersion at upper and lower wavelength limits means that this is lower wavelengths and upper wavelengths, and the dispersion will be almost linearly increased with wavelengths. So you will place WDM signals such style. So the maximum chromatic dispersion at upper and lower wavelength limit is used to define the maximum uncompensated main path. That means around here or here, or max or minimum. And for wavelengths between the upper and the lower of the wavelengths, and the maximum dispersion is linearly interpolated between the values given the extreme wavelengths. That means that just at this range of wavelengths, we can consider that dispersion is linearly increased. So we can say, yeah, this is almost linear. So the required maximum dispersion tolerance at the upper and the lower wavelength limits is set to a value equal to 1.05 times. This is just margin or something like that for target distance. So these dispersion values are considered a practical upper limit for field deployments with distances at about relevant target distance. This is just a simple thing that you will define the upper limit and the lower limit, and you can dispersion has a, you can consider dispersion has a linear increase as wavelengths. Okay. And another optical path parameter is the reflections. So reflections are caused by refractive index discontinuities along the optical path, so disturbing effect on the operation of the optical source or amplifier, and multiple reflections, which leads to interferometric noise at the receiver. That means that if we have a reflection in a fiber or something, of course it will lead to degradation of the signals. But not only degradation of the signals, it will cause some trouble to such an optical source or amplifier, like kinds of active device, because active devices are very weak for reflection or some disturbance. So the optical return loss is the ratio of the incident optic power to the total return optic power from the entire fiber. It's really straightforward. And in the fiber, the reflected power is almost due to the Rayleigh scattering. Rayleigh scattering is, we cannot avoid the Rayleigh scattering in a fiber, but actually backward scattering is so less problematic in optical fiber transmission. And instead, we can use this Rayleigh scattering for OTDR measurement of optical fiber. So you can see the optical signal propagation inside the fiber by OTDR technique. This is due to the Rayleigh scattering, Rayleigh back scattering. And the reflections from the optical path are controlled by specifying the minimum optical return loss of the cable front at the source reference point, including any connectors, or the maximum discrete reflectance between S and R reference point. Yeah. And if the maximum number of connectors was a discrete reflection points included in the optical path must satisfy the specified overall optical return loss. And if this cannot be done using connectors meeting the maximum discrete reflections requested, then connectors simply have to replace, or simply you have to decrease the number of connectors. For example, you directly use fuse splice connection instead of fiber connector, or like that. So another optical path parameter is the maximal differential group delay. This is so-called polarization mode dispersion. But this polarization mode dispersion is more in detail described tomorrow's chapter 7. So I don't describe here, skip now. So the next one is the interface at point MPI R. R means so receiver side. Again, we define the input power. We also define the input power at the MPI sending side. And again, we will define the optical power at the receiver side. So mainly maximum mean channel input power means the maximum acceptable value of the average received channel power at the point MPI RM or R to achieve the maximum BR of the application code. So minimum mean channel input power means the minimum value of the average received channel power at the point MPI RM. The minimum mean channel out power minus maximum attenuation. That means just sending power minus optical attenuation due to fiber loss. And next one, the maximum mean total input power. This is relevant only in the case of multi-channel operation, which the maximum acceptable total input power. This means that in a single channel transmission system, that channel power equals total power. But in the case of multi-channel systems, channel power is different from total input power. And sometimes too large optical power cannot be accepted by receiver. So this acceptable total input power defined here. And this is the interface at point MPI-R and MPI-R minimum receiver sensitivity. So originally, the minimum receiver sensitivity is the minimum value of the average received power at point MPI-R to achieve the specified maximum bit error rate of the application code. This is just say receiver sensitivity or minimum detectable receiver power. So in most cases, the minimum receiver sensitivity is specified at a bit error rate of 10 to the power of minus 12. Yeah, this value is commonly used in recommendations nowadays. But bit error type of application code define the bit rate of 10 to the power of minus 10. But we don't use now such worse bit error rate for specifications. So this must be met with the transmitter with the worst case values means I mask, extinction ratio, return loss, connector degradation, amplifier noise measurement tolerance that I described before. And this does not have to be met in the presence of a dispersion or reflection from optical bus. That means this receiver sensitivity is defined only this. So back-to-back configuration from transmitter to receiver, no other impairment factors. Yeah. This is the minimum equivalent sensitivity. The minimum sensitivity required by received at MPI-RM multi-channel interface to achieve the specified maximum below of the application code if only one channel was left at point MPI-RM. Do you understand the difference between this minimum receiver sensitivity and the minimum equivalent sensitivity? No? A bit confusing. Yeah. This means that minimum receiver sensitivity considers only one single signal channel. So one signal channel, for example, minus 20 dBm signal channel can detect the rule, and bit error rate is better than 10 to the power of minus 12. In that case, minimum receiver sensitivity is minus 20 dB or so. But in case minimum equivalent sensitivity is adopted for a multi-channel system, at the point of MPI-R, you will see so many wavelengths. And you can't detect only one signal channel at this multi-channel interface. So this is just equivalent, means that if you, when you assume that only one wavelength is pick up and the other wavelengths will be removed, in such a case, you can say equivalent sensitivity. But don't care about so detailed about this terminology. Okay. And next one is at receiver end, maximum optical path penalty. Path penalty means something penalty we have to pay for the transmission of fiber. The path penalty is defined in 959.1 as a reduction of receiver sensitivity for equivalent sensitivity or equivalent sensitivity in the case of multi-channel applications due to distortion of the signal waveform during the transmission over the path. This causes a shift of the system's BER curve towards higher input power levels. Yeah, I showed the example of this image. That if we have no such a penalty, for example, we have such a BER curve. But if we have some penalty due to a transmission, this BER curve, this is a received signal and the bit error rate will shift toward the right side, Right side means this degradation. So positive path penalty is common, but in some cases, negative path penalty may exist under some circumstances, but generally expect it to be sufficiently small. So this means almost all the case path penalty is positive and always degrades this curve. And the idea is that VL curves should be shifted only towards the higher receiver input power levels. This is higher levels. But shape variations of the VL curves are not uncommon. So the path penalty is defined at the bit error rate level 10 to the power of minus 12 here. This curve will change depending on the bit error rate. So we have to define any specific bit error rate to say about this penalty. So continue the description of optical path penalty. As you can see in this figure, this is this idea of optical path penalty. So this is a receiver sensitivity. This could be defined without any penalty. So from sender, just loss, and receiver. So we can define receiver sensitivity. But if there could be any impairment, degradation of the signal due to optical signal transmission, so we have to add some optical path penalty, 1 dB or 2 dB on this receiver sensitivity. Then we can get the minimum input power. This minimum input power is a bit higher than receiver sensitivity, because this receiver sensitivity actually defined with no degradation of the signal, just noise of receiver noise. Yeah. So we need some increase of optical power to cope with this penalty. This is the meaning of optical path penalty. So some application cause requiring FEC byte to be transmit both receiver sensitivities with or without degradation due to optical path measured after the error correction has been applied. And the maximum path penalty of 1 or 2 dB is defined for applications with channel bitrate corresponding to 2.G or 10G. And the actual value depends on the application and the bit fiber type. Of course, signal degradation or waveform distortion depends on the fiber type G.652 or 655, like that. And actually, the path penalties are not made proportion to the target distance to avoid operating systems with high penalties. That means that the path penalties are not in proportion to the distance. That depends on the situation. So path penalties associated with optical paths are contained in the maximum optical path penalty, but not in the minimum receiver sensitivity. This is the same meaning as I described before. And the maximum optical path attenuation is the difference between the minimum transmit output power and the minimum receiver sensitivity, additionally reduced by the value of the optical. This is the same meaning as I showed in this figure. This is just minimum output power and the minimum input power, just the difference between this receiver sensitivity is called optical penalty. So I roughly, briefly reviewed the specification of interface at point MPIS and optical path penalty, optical path, and MPIR point. So I will finish chapter 6 at this page. This is just an example of optical interface specification, actually described G.959.1. For a single span DWDM system with 32 channels operating at 10G and the C band and G.652 fiber. Actually, this is just general information. Number of channels is 32, energy 10G, and the bit error rate could be 10 to the power of minus 12. The fiber is 652. As I described, the interface at point MPI S means the sender side. So channel output powers, total output power, channel frequency is the wavelength of the signal. And channel spacing is 100G, actually 0.8 nanometer spacing in DWDM system. spectral excursion, allowable spectral excursion is 20G, or channel extinction ratio is 8.2 dB. IMASC is defined at that figure. And as I shown, optical path parameter between S and R. Maximum attenuation is 11 dB, minimum may be 0. And the maximum chromatic dispersion at the upper wavelength limit and lower wavelength limit is maybe 800 for G.652 fiber, and also 800. So minimum optical return loss, sorry?
For this table, for interface at point, MPISS, line 1 and 2. I don't understand the difference because you are talking about minimum mean channel output power, and then again minimum mean channel output power. One value is 0 and another one is plus 3.
Power? In this table?
It's not the same. The table in the handbook and the presentation there is a
different?
Yeah, there is some confusion.
Really? Actually,
can you have a look?
Sorry?
Come and have a look.
Okay. Any mistakes? So 32 channel means 32 wavelengths. That is 32 is, if log scale, dB, what? Answer is 15. In dB scale, 32 channels, 50. It's very clear if 10 channel, 10 log 10, 8, 10. Yeah, 10. 10 channel, 10 dB if I say dB scale, 10 dB. So each channel has 3 dBm. 3 dBm multiplied 32 means summation of in dB scale. Summation means 30 dBm plus 15, so 18. Okay. Just a simple log scale calculation. So this tutorial is so long time. You may be a bit tired, so sometimes your head is confused. Such a manipulation of numbers, right? I understand. And really, you have already 1 week. you already have 1 week tutorial, and we are now in another week, so you will be so tired. Yeah, I understand your situation. But anyway, this is our job. We have to do it. Okay, so almost 4:30, so I will finish here. This is just transmitter side and optical path penalty, minimum receiver sensitivity. And this is just receiver side, receiver power and equivalent sensitivity, minus 30 dB. And reflectance is minus 27 dB. This is just an example. So I will finish here of chapter 6. So do you have any questions? Okay? Okay, thank you very much. Thank you very much, everyone. So we will start chapter 7 tomorrow morning. What time is it okay? 9 or 9:30? 9? 9 is okay? Okay. So shall we start chapter 7 tomorrow morning at 9 o'clock? Okay, thank you very much, everyone.